Right, this is 5.1b on log differentiation. So a warm-up problem here is if g of 2 is equal to 3 and g prime of 2 equals negative 4, find f prime of 2 if f of x equals x squared natural log of g of x. So we want to find the derivative. However, some of these terms are stuck in function notation, so we have to work within their restrictions within the context of this function notation, and then we can use these order pairs to help us find the derivative. So the rule that we learned from the previous lesson is our derivative for natural log of u is u prime over u. But here we have x squared natural log of g of x. These are two separate functions. X squared is the first, ln of g of x is the second. These are being multiplied, so we have to go through product rule. So f prime g plus f g prime. So x squared becomes 2x. F prime g plus f g prime. So the derivative for ln of g of x is simply g prime over g. We're just following the rule here, u prime over u. So we found the derivative. Once we find the derivative, we want to evaluate the derivative at x equals 2. So replace all the x values with 2. So we get 2 times 2, ln of g of 2, 2 squared, g prime of 2 over g of 2. All right, so let's see if we can evaluate this one by one. 2 times 2 gives us 4. Ln of g of 2, now g of 2, we go back to our values here. G of 2 is 3. So we take out the g of 2. In place of it, we put a 3. All right, that's the first portion, plus 2 squared, which is 4. And then g prime of 2 over g of 2. Now g prime of 2 is negative 4, and g of 2 is 3. So we can simplify this a bit more. So 4 ln of 3 minus 2 squared times negative 4 is negative 16 over 3. So this is our derivative at x equals 2 for our function f of x. All right, log differentiation is our topic for today. Log differentiation is simplifying a non-log function using log properties to expand before differentiating. So with log differentiation, we're introducing logs into the problem that initially does not have logs. And the reason why we want to do that is because we want to take advantage of these log properties so that we can expand, making a complex problem a little bit more manageable, because we are hopefully able to expand them into smaller portions. So here are the steps we're going to take with log differentiation. Again, we're introducing logs into a problem that initially does not have any logs in it. So that's something to keep in mind, is we don't do log differentiation if there's already natural log or log base 3 or any log expression that is already in the problem. We're doing this to problems that does not have any logs to begin with. Hey, so first step with log differentiation, we take the natural log of both sides. We introduce logs to both sides of the equation to maintain balance of equation. We do that to both sides. Next step, we look at the right side. We simplify and we expand using log properties, whether it is product, quotient property, or power property. We expand as much as we can on the right side. On the left side, we're going to use implicit differentiation because this natural log of y that takes place on the left side of the equation, we have to, y is no longer by itself, so the derivative processing requires implicit differentiation. And then finally, we substitute and solve for y, replace y rather, but really we're trying to find dy dx. Example 1. Find the derivative for y equals x minus 2 quantity squared all over square root of x squared plus 1. Normally, if you find the derivative, maybe you would want to use quotient rule and chain rule, but we're going to try to find the derivative for this using log differentiation. So to follow the steps here, we take the natural log of both sides of the equation. We introduce logs into the problem. So you see that with natural log of y, natural log of this entire expression. Next step, we want to try and expand this as much as we can using log properties. So this is ln of a over b. We can rewrite that as ln of a minus ln of b. Now these exponents can come down in front. Once they come down in front, now this is a lot more manageable in terms of derivative rules rather than trying to apply derivative rule at this point. So let's take care of the left side here. ln of y, the derivative for ln of y is simply 1 over y. We're involving y's derivative, so we have to attach dy dx. Okay, now on to the next expression. So 2 as a coefficient stays. ln of u becomes u prime over u. So x minus 2's derivative is 1 all over x minus 2 minus. Again, another log expression. So 1/2 stays. ln of u becomes u prime over u. So 2x over x squared plus 1. We can distribute the 2 through, move the y over to the right side, and then finally replace y back in terms of your original equation in terms of x. Okay, so we have our derivative here using log differentiation. Right. Example 2, find the derivative for y equals x to the 2x plus 3. Now, this is a problem where we have to use log differentiation because we don't have a rule that allows us to find the derivative for a variable raised to another variable. So what we're going to do is we're going to take the natural log of both sides. Use log properties. We have ln of a to the n. This exponent can come down in front, so we have all that 2x plus 3 times ln of x. Now we can find the derivative, so ln of y, again, implicit differentiation, 1 over y dy dx. 2x plus 3 and ln of x, these are two separate functions. We have to go through product rule. So f prime g plus f times g prime. So once we have that, then we want to solve dy dx, move the y over to the right side, and then replace y back in terms of x, in terms of the independent variable x. Just a small minor rule here. We have the rule for ln of u, and the same rule applies for ln of absolute value of u. ln of absolute value is simply u prime over u. So in a quick example here, find the derivative for natural log of the absolute value of x squared minus 5. We apply it the same way as natural log of u. So 2x squared minus 5 becomes 2x. X squared minus 5 is the u value. So u prime over u, we're going to treat this the same way that we would as ln of u. Example 4, locate any relative extrema and inflection points for y equals x over ln of x. So curve sketching problem, we have to go through and use first derivative rule as well as concavity test, first derivative test, sorry, and concavity test. So to get to that, we have to find the first derivative. So first derivative, if you see this is x over ln of x, variable divided by another expression, so we have to go through quotient rule. So f prime g minus f g prime all over g squared. Clean this up a little bit. We get ln of x minus 1 over ln of x quantity squared. Remember, if you want to find critical points, they can come from both the numerator and the denominator. So we set the numerator equal to 0. ln of x minus 1 equals 0. ln of x equals 1. ln of x, we can rewrite this as log base e, so e to the 1 is equal to x, so there's a critical point at x equals e. And then another one, if we set the ln of x squared equal to 0, we get e to the 0 is equal to x, which is not going to result in a critical point. So natural log of x equals 0 will not produce any critical points there because we know 0, there's a vertical asymptote. So that's why only critical point is at x equals e. However, natural log of x is equal to 0. Sorry, rather, ln of x is equal to 0 when x is equal to 1. So take that back here. Natural log of x equals 0 at x equals 1. So we have 1 being also a critical point. So if I have natural log of 1, that will give us 0. So we have that as critical point. 0 is there because we know the graph is never going to exist to the left of 0. Natural log of x is equal to, when x is 0, that will cause this to be undefined. So we have that as a starting point for our graph. Now we have, we want to test each of these values, each of these intervals with the first derivative. So if I plug in 0.1, I'll get a negative over a positive, which is negative. If I plug in 2 for instance, if I plug in 2, which sits between 1 and e, I'll get ln of 2, which is a positive value that's less than 1. So negative over a positive. So again, this portion is negative. If I plug in 3, ln of 3 is a value greater than 1. Minus 1 is positive over positive, so positive. So we follow the graph. The graph has a vertical asymptote at x equals 0. The graph is going to fall, decrease until we get to 1, level out, and then keep decreasing, and then hit a relative minimum, and then increase to infinity. So we can say relative minimum occurs at x equals e, and then that y value, we simply plug e back into the original function. So e over ln of e is simply e. So relative minimum is at e. To find the second derivative, we look at the first derivative and we go through quotient rule again. So f prime g minus f g prime. This whole thing is g prime using chain rule all over g squared. Factor out the 1 over x. Combine like terms on the inside. 1 of the ln of x cancels out. We're left with negative ln of x plus 2 all over x ln of x quantity cubed. We set the numerator equal to 0. When we do that, we get x equals e squared. Again, the critical points will exist at 0 and 1. At 1, natural log of x is 0. And at 0, because we can't have 0 in the denominator. So we test each of these intervals with the second derivative. If I plug in 1/2, I'll get negative plus 2. This value is less than 2. So we have positive over a positive, which is positive, so concave up. If I plug in 2, for instance, I'll get a value that's less than 2, so positive over positive is positive. If I plug in more than e squared, let's say e cubed, so ln of e cubed, bring down that 3, the natural log of e cancels out, so negative 3 plus 2 is negative over a positive, so negative. Concave up, concave down. 2 critical points at 1 and e squared, but there's no change in signs at 1. There's only a change in sign at e squared. So our point of inflection will simply be at e squared because y double prime changes signs. And if we want to find the y value, we plug e squared back into the original equation. So e squared over ln of e squared will give us 2. So e squared over 2. Ordered pair here, point of inflection for our graph f of x.